In this lecture segment, we'll look at the code world's simulation and at the animal base class. We'll be looking at animal class members and methods, also talking a bit about static inner classes, and do a little bit more on the initialization of static member data. Now to start with, let's look briefly at the running Code Worlds app to get some context before we go over the code. This first version is pretty simple, but not too bad for less than 500 lines of code. Later versions will be more sophisticated. Our world, as you can see in this sample run here, is a two-dimensional grid of locations. In this example, it's 20 by 20, but that's configurable in the input file. And Code Worlds displays the grid textually with dots for empty spaces, and a letter plus an identifying digit for simulated entities. And again, that's pretty simple. We'll leave graphical displays for later versions. In this example, the C and some number markers are for cows, and the H and some digit markers are for horses, and the T up here, that's a tree. Now, the entities can all move, well, except for the tree, as you can see by stepping the world from time point to time point by hitting return. Each time you do, Code Worlds advances the simulation by one step. Think of it as 1 second of time, as you like, as labeled up here. And then it reprints the grid. If you arrange the display correctly, each reprint falls in the same position as the prior one. This is actually the end of a long run of output that I've been creating. But again, if you arrange it correctly, then each reprint falls in the same position as the prior one, and you get a kind of primitive stop-action movie out of it. Okay? Now the animals, if you look, will all move steadily in straight lines, but they keep from going off the grid by turning to the right. And if I run the simulation long enough, they'll also exhibit herding behavior. And you can see the cows there starting to move together, and the horses will get together in a minute. And there we go, as they bounce around. And by the way, you can see how the vector class that we've been working with might fit in here. The locations and the velocities of the animals are both vector quantities, as we'll discuss in detail in a minute. So, now that you know how it works at a high level, let's look at the code. So, cows and horses and any possible future animals have a lot in common. They all have locations, velocities, and identifying numbers, for instance. So it makes sense to put all that into a base class, animal, that provides methods and members that will be common to all animals. Now once we have that, we'll create subclasses for each specific type of animal, customizing each by adding members and methods and perhaps overriding methods from animal. So skipping to just above the constructor in animal, we can see that we have an ID number for each animal and 2 vectors, here and here. Let's talk about those. First of all, there's vector loc, the second one. Now this holds the animal's location, with its x value being the column in the display and a y value the row, in increasing y order, by the way, upside down from the usual xy plane. So returning back to our diagram, this is increasing x, and downward is increasing y. It is upside down from the usual xy plane. This rule makes it easier to put animals into two-dimensional arrays, where rows increase downward, and it matches common conventions in computer graphics. Now, loc will be a margin vector, because we want approximate equality checking for locations. And that brings us to question 1. Loc is declared as vector. How can it be a margin vector? Coming back from a pause there, this is really just a review. A vector reference can refer to a margin vector. A margin vector is a vector. We'll just have to be sure we arrange for loc to do so. And we'll do that in the constructor, which, as you can see, requires a margin vector for loc. Now, vector VLC holds the animal's velocity. The amount will change its location in x and y for each step of the simulation. A VLC value, for instance, of 1.0 minus 1.0 would make the animal move to the upper right in our simulation. Remember that x is columns, y is rows, and y increases downward. The animal constructor is pretty straightforward, as are the getters and setters here. Though do note that the setter for location does demand a margin vector again, so we'll be sure that location is assigned a margin vector to point to. You can ignore, by the way, the override attributes here for the time being. We will get back to that later, and we'll explain what they are overriding when we do. Now, before we look at the main animal logic in the method step down here, we want to go back up to the top of the class, rewind a bit, and look at the range class right here. Notice that it's inside of animal. That makes it an inner class, and animal is its outer class, range's outer class. Now, classes may be declared inside of other classes in Java and most other object-oriented languages. And this is done for classes that are used only by one other class. Range, for instance, describes the rectangular range within which animals may roam. Its members define the upper and lower limits for x and y. Range is only used within the animal class or by other classes calling animals' setRange method down here. In such cases, good design makes range an inner class of animal, so it's grouped with the animal methods and members. Now, an inner class may be private and thus accessible only within its outer class, or it may be public and accessible anywhere. Protected is also an option. However, if code outside of animal accesses range, it must do so with scope. It has to refer to animal.range. An inner class public or private accessibility determines who can declare references and allocate objects of the inner class, but it doesn't determine the access of the individual data members of the class. A public inner class, like range, may still have private members. The static keyword in range's declaration is important. It makes range a static inner class. And aside from the ability to be made private and the requirement that code outside of the outer class use scope to access it, a static inner class is no different from any other class. If you're familiar with inner or nested classes in C++ or C# or other languages, then Java static inner classes behave the same way. So you can use a public static inner class just like any other class, except that you have to add animal dot if you're not within the animal class. However, without that static keyword, then range becomes an instance inner class, which has much subtler behavior that we'll cover later. Java instance inner classes are in a class of their own, so to speak. No other language that I know of has inner classes that behave like them. For now, we'll stick with static inner classes. And if you are new to inner classes or nested classes, be sure you understand that putting range inside of animal doesn't mean that animal necessarily has a data member of type range. All you get for the inner class declaration is the type. If you want a range object as an animal member, you have to declare a range reference and allocate a range object per usual. For instance, animal has a static range member right here, and that is settable via the static method setRange. And a question here to think about: what would the method call look like for an outside class to set the range for all animals? Assume that low x and low y should be 0 and high x and high y should be 42. Don't forget scope. Write the code that you would use in, say, a main program to set the range for all animals, given what we've said. So there are a couple of ways you could do it. You could have used a couple of different statements, but the briefest way to do such a thing from outside of animal would be to write animal.setRange and then pass it a range that you construct, allocate and construct on the fly here, and there you'll have to use animal.range as the name of the class, and there's the constructor arguments. So when you did this, did you get both of the animal prefixes? You need the first because setRange is static, and the second because range is static. But what happens if no one ever calls setRange? Shouldn't we at least initialize range to null in the animal constructor? Go down here. If that never got called, never got initialized by setRange, shouldn't we put a null assignment like that in here? So question 3, why is this not necessary and also a really bad idea? This isn't about inner classes, by the way. This is just about static member data. Returning from a pause. Well, first of all, Java initializes all member references to null, as mentioned in an earlier segment, and that includes static member references. So you've already got the null for free. And then second, if you wrote range equals null in the constructor, then every time an animal object was created, and the constructor got called, then the one static range reference that is shared among all animals would be set to null, wiping out the effect of any call of setRange. So we don't want to do that. Okay, now that we have the preliminaries out of the way, the step method is relatively easy to understand. It assumes that one time unit has passed, so it creates a new potential location for the animal by adding the velocity to the location. It then sets loc to that new location as long as we either have no range to worry about, or we have one, but the new location is within the range. Now, if that's not so, then step instead leaves the location unchanged, and it turns the velocity by 90 degrees to the right by negative pi over 2 radians. Now, animal overrides toString to produce a label that can be used in the textual display, for instance, C1. Now, the logic is simple. It concatenates a letter label returned by getLabel to the ID. But here is the most interesting OO point, or one of the most interesting ones in animal. getLabel returns question mark, which is never actually meant to be used. Instead, as we'll see when we look at the subclasses of animal, they all will override getLabel to return the right sort of letter, a C for a cow or an H for a horse, for instance. And they won't override toString, they'll use the animal version. So we'll have, for instance, a cow object calling the animal toString, which in turn will call the overridden getLabel in cow to get a C label, and ultimately then return a C and ID string. Now we'll look at this from the other side when we get to the subclasses.